So a quick reminder, an intercept is where a graph crosses an axis, whether it's the x-axis or the y-axis. So a point at which the graph of a function intersects an axis is called an intercept. An x-intercept is the x-coordinate of a point where the graph crosses the x-axis. Oppositely, a y-intercept is the y-coordinate of a point where the graph crosses the y-axis. So you only need to mention either the x value for an x-intercept or the y value for the y-intercept. You don't need to mess around with the other one. But if you were talking about what the other one was, the other value would be 0, because when you have an x-intercept, the y value is 0. When you have a y-intercept, the x value is 0. A linear function has at most one x-intercept, while a nonlinear function may have more than one x-intercept. No function will have more than one y-intercept. I want to talk about that real quick. Why would a function never have more than one y-intercept? If we look at number 18 from lesson, this is from the assignment 1-1. You didn't do this problem, but we've got a y-intercept here, here, and here. And it says no function will have more than one y-intercept. So what does that suggest about this? It's not a function. How come? Okay, going back to what we were talking about at the beginning of the lesson in like the vertical line test back in lesson 1-1, why would this not be a function? Not necessarily that, but right here, a relation is a function if all the x values are different. So if you have repeated x values, it fails the vertical line test. You get multiple points when you lay a vertical line over the I'm not gonna say function, when you lay it over the graph, which means that it isn't a function at all in the first place. And so if we go back to where we're at now, page 15, no function will have more than one y-intercept. If a graph has more than one y-intercept, you can have a graph that looks like that. It just means that that graph is not a function. Okay. Example 4 then. It says use the graph to estimate the x and the y-intercepts. So I don't think we'll need to estimate on this one, but if we needed to, we would. The graph intersects the x-axis at what point? What are the coordinates of the 0, 0? Yeah, right in the middle. And so we're looking specifically for the x-coordinate here. So the x-intercept is 0. The graph intersects the y-intercept at what point? 0, 0. Yeah, it goes right through the middle of the graph. This time, the y-intercept will be equal to the y value. They happen to be the same here, just because it goes through the origin of the graph. But identifying x and y intercepts, you've done this before. Okay. What about this thought over to the right-hand side? Describe a line that does not have two distinct intercepts. Can you have a line that is a function that only crosses one of the two axes? And what kind of a line would that be? Meaning what? Okay. I would maybe argue against the straight up and down, because I'd probably argue that that isn't a function. But in terms of horizontal, yeah, a horizontal line only crosses the y-axis. It is a function. A vertical line, it only crosses the x-axis, but it's not a function because you've got repeated x values. So yeah, horizontal line would be the answer for this one here. All right, example 5. Use the graph to estimate the x and y intercepts. All right, let's talk about this one. Then I'm going to have you do A and B on your own at the bottom. So the graph appears to intersect the x-axis at, just go ahead and plot these. The x-axis would have an intersection here and here and here. 3 points where the graph comes into contact with the x-axis. That would be the point -3, 0, -1, 0, and 2, 0. So there are 3 x-intercepts of this function, and those are values of -3, -1, and 2. If you are looking at a function on a graph, it can have at most 1 y-intercept. So this graph appears to cross the line. This graph appears to cross the y-axis. Down here, right up here at, what number is that? 12, 0. Yeah. Why is it 12, 0 and not 3, 0? They're going up by, every line is 4, right? Oh. Yeah. 4, 8, 12, 16. So this would be the point 0, 12. Which means we have a y-intercept of 12. Great. So for A and B, I want you to answer those real quick. You do not need to write out the coordinates like we have here or here. All you need to do is state the values where each graph crosses the x-axis and where each graph crosses the y-axis. For the y-intercept, you will have at most how many numbers for the y-intercept? 1. There will never be more than 1 y-intercept if it's a function. So answer A and B real quick. I'm going to give you 1 minute to do this. Yes. Yeah. Because each line represents the work you get. Everybody's here today. All right. And everybody was on time. Nice job. Pretty rare thing for a first period class to have everyone here and everyone on time. So well done. All right. Let's have ourselves a look. Where does this line cross the x-axis? -5. So 1, 2, 3, 4, -5. You got it. X-intercept, -5. How about the y-intercept? 2. All right. Before I ask the answer for the x-intercept or intercepts, let's go with the y-intercept here on the second one. 0. All right. My next question is not what is the answer for the x-intercepts, how many are there? 5. And it can be helpful. I mean, I did this on the example as well. If you want to put points on there just to make it really clear how many there are, it's never a bad idea. So let's see. We're going to -4, -2, 0, 3, and 5. Cool. Any questions about that? Nice thing about x and y intercepts, you can literally point to them when they're on a graph. All right, turn the page. All right. Interpret the meaning of intercepts. What does it all mean? Ricardo launches a rocket from a balcony. That sounds like fun. The table shows the height of the rocket after each second of flight. Okay. Identify the x and the y intercepts of the function that models the flight of the rocket. Okay. So in the table, the x coordinate when y equals 0 is the x coordinate when y equals 0. What's that? That would be the y coordinate when x equals 0. but we're looking for the x coordinate when y equals 0. So y equals 0 is here. So if you want to, you can say, all right, here's x, here's y. When y is equal to 0, yeah, x is equal to 8. Thus, the x-intercept is 8. Conversely, in the table, the y-coordinate when x is equal to 0 is 15. Thus, using strong language here, thus, the y-intercept is 15. All right. Now, what does this mean? What is the meaning of it all? What is the meaning of the intercepts in context with the rocket's flight? So the x-intercept, what does that represent? By the way, the x-intercept is when y is equal to 0, so that was 8. The x-intercept is the blank after the rocket is launched that it returns to ground. What is 8? What do the x values represent here? Time, okay. So, and the y values are what? What do the y values represent? Height, okay. So, rocket launches, goes up, comes down. So at a time of 8 seconds, it has a height of 0. So what does that mean? If something hits the ground, that means the flight's over, right? So the x-intercept would represent, what's that? Yeah, the length of the flight, yeah. It takes 8 seconds for the rocket to come back down to the ground. So the x-intercept is the time. The time in seconds, the number of seconds after the rocket is launched that it returns to the ground. The y-intercept, that would be the point at the top. Where did he launch it from? A balcony. Are balconies on the ground? No. So that's why when time is 0, before he even launches it, it already has a height because he's not launching it from the ground, he's launching it from a balcony. So the y-intercept is the what? The height, yeah, from which the rocket is launched. Cool. Let's see. We're good there. Okay. Any questions about intercepts so far? So you can tell an x and a y intercept from a table of values based on when x is 0, that would be the y-intercept, and when y is 0, that would be the x-intercept. So if you want to put a little note here, that is the y-intercept, and right here is the x-intercept. When x is 0, the y value is the y-intercept. When y is 0, the x value is the x-intercept. Okay. Now we're going to talk about what we saw on that explore activity, that warm-up that we saw yesterday, the idea of symmetry. We talked about line symmetry and we talked about point symmetry. Line symmetry is if you have a particular line, it could be horizontal, it could be vertical, it could be diagonal, but as long as every point on a function reflects perfectly across that line and you still end up on the function, that would indicate line symmetry. Point symmetry is a little more specific because point symmetry says you have to rotate the graph 180 degrees in order for it to map back onto itself. Now that point doesn't necessarily have to always be the middle of the graph, but it does have to be somewhere on the graph, and it does have to be a 180-degree turn for that to work. So a figure has symmetry if there exists a rigid motion. A rigid motion would be a transformation, whether that's a reflection, a translation. Remember, translation just means you're moving it around. A rotation. A glide reflection is something that if you were in my Geometry B class last year, we talked about. Glide reflection basically means that you would like move it and then you would reflect it. But those are all rigid motions, and a rigid motion just means you're doing something to a figure, but you're not changing the size. You're not making it bigger or smaller, but you are moving it around or flipping it or rotating it or doing something like that. Everything but changing the size. So it maps the figure back onto itself. So if we're talking about line symmetry, it means that a graph has line symmetry if it can be reflected in a it does say vertical here. I guess we're only talking about vertical. That's nice. Narrows it down, so we don't need to worry about diagonal right now. That's fantastic. That'll make it easier for you. Line symmetry if it can be reflected in a vertical line so that each half of the graph maps exactly onto the other half. That's really convenient. So you're only looking for vertical line symmetry. So basically, if a point reflects horizontally across that line, you're good. The line, so description, the line dividing the graph into matching halves is called the line of symmetry. Every parabola has one of those. You learned that back in Algebra 1. That would be called the axis of symmetry when you're dealing with parabolas. But in terms of line symmetry, that would be the line of symmetry. Each point on one side is reflected in the line to a point equidistant from the line on the opposite side. So basically, point A is 2 away from the line of reflection, which means at this point over here, A prime, that's what the apostrophe means there, point A prime is also 2 points on the opposite side. Down here, this point is 1 away from the line of symmetry. If you go to the right, that point is 1 away from the line of symmetry. They're equidistant. So that would be line symmetry. In terms of point symmetry, a graph has point symmetry when a figure is rotated 180 degrees about a point, so 180 degrees around some point on the graph. So it's like, I'll use this as an example. So a point would be anywhere. So like if you drop a point somewhere and you literally just spin it around that point, that would be point symmetry. Now, the point could be in the middle, or maybe in the case of this ruler, the point could be right here on that hole punch, and you can spin it around that point. If you turn it 180 degrees and it maps perfectly onto itself, that would indicate point symmetry. So the point about which the graph is rotated is called the point of symmetry. Sometimes it's in the very middle of the graph, like here. Sometimes it's not. The image of each point on one side of the point of symmetry can be found on the line through the point of symmetry equidistant from the point of symmetry. So essentially what that means is if we go from A to this point here, we'd be going down 2 and back 1. Or I guess down 2 and left 1. So you need to use the opposite, like the opposite slope in order to make that work. So instead of down 2 and left 1, from here we're going up 2 and right 1. Okay, so that's how we're going to be able to deal with point symmetry. Point symmetry can be a little bit harder to figure out sometimes just because of that particular thing. But I'll show you some ways to kind of figure out maybe a little bit easier how to make that work. So let's keep going. A little bit more even versus odd functions. This is where you're going to learn something brand new. This is not necessarily something super complicated. Now, the notation can be a little bit tricky, but I'll be able to explain it to you in just a second. So it says functions that have line symmetry with respect to the y-axis are called even functions. Basically, what that means is the ends of the function are going in the same direction. Okay, if both are going up or both are going down, that would be an even function. What this notation right here means is if you have an x value, a function for an x value, those two things, so f of opposite x and f of x technically are both y values. So it's saying given opposite x values, you still have the same y value. That's what that means. So right here, given opposite x values around a line of symmetry, the y value is the same. So if we imagine this is the middle of the graph, if you have a negative, this is 2 to the left of the line of symmetry. So that would be a -2 in context with that line of symmetry. This A with the apostrophe A prime would be a +2 in context with the line of symmetry. So the x values in relation to the line of symmetry are opposite of one another. -2 here, +2 here. Those are not the actual x values. Those are the x values in context with that red dotted line. However, the y values are identical. They're the same height. So around a line of symmetry, the x values are opposite, but the y values are the same. That's what we're saying. That would be an even function. For an odd function, the ends are doing different things. One's going up, one's going down. And you can think of, I mean, most even functions are not onto, and most odd functions are. That's a good way to think about it sometimes. So functions that have point symmetry with respect to the origin are called odd functions. Now, this is, first of all, this is not an even function. I just want to make that clear. It is not an even function. Now, I was using this as an example, but this is not an even function because it does not have line symmetry with respect to the y-axis. It has line symmetry with respect to this red line. So I was giving you a little bit of an example about what that looks like. In order for something to truly be an even function, though, it must have line symmetry specifically with the y-axis. It can't just have line symmetry. Okay, it's got to be specifically on that. It's like a special type of line symmetry, kind of like odd functions specifically have to have point symmetry with the origin at 0, 0. So if you flip it around the origin and it's the same facing either way, then it's an odd function. And just in terms of what this means right here, I'll go ahead and let's see. Let's say this is the point 2, 3. Let's say this is the point 2, 3. Let's just go ahead and put that on our graph. 2, 3. This point down here would be the point -2, -3. So what we're saying is, if the x values are opposite values of x, the f of x values are also opposite. F of x, opposite f of x. So if the x values are opposite, the y values are opposite. 2, -2, 3, -3. Both x and y values are opposite of one another. That's what it means to be an odd function. All right. Identify the type of symmetry of each graph. Let's take a look here. F of x is equal to 3x plus 1. Does this one have, so again, with line symmetry, we're only talking about vertical lines. Is there a vertical line that you could draw through this and place them on opposite sides of that vertical line and have it look exactly the same? Is that a possibility? So if we were to put a vertical line somewhere on here, pencil, let's say we put a vertical line right here. I've got a point here, and if I reflect this point across the vertical line, that goes here. Is that on the function? No. So this one does not have line symmetry. There's nowhere on here where you could place a vertical line and reflect it across that vertical line left and right to create points that are on the line. Straight up diagonal lines like this are not going to have line symmetry. That's not going to work. How about point symmetry? Could you rotate this 180 degrees and have it look exactly the same? Yeah. So, and because it's a line, it has point symmetry literally everywhere. You could choose any point on here that you want to. We could choose the y-intercept if we wanted to. So there's our point, right? If we spin it around that point, we can go over 1 and 1, 2, up 3 right here. So right 1, up 3, which means if we go left 1 and down 3, we should have a point on the function as well. Left 1 from this point here. Left 1 and 1, 2, down 3. There it is. So It also just gives us the answer. Point symmetry, a 180-degree rotation around any point on this graph is the original graph. So lines, linear equations always have point symmetry. Okay, second one. Point symmetry, line symmetry, or neither? If we flip it upside down, is it exactly the same as the original? No, because it's facing up instead of down. So it's not exactly the same. Is there a vertical line that if we draw through there, it would end up folding perfectly onto itself? Yeah. Where is that vertical line? What's the x value of that vertical line? -2. Yeah, it tells us. And it's -2 because on the x-axis, every value is going up by 2. So this would be line symmetry. Because the reflection across the line y equals -2 coincides with the original graph. Every point on the left and the right side of that red dotted line matches perfectly onto the original function. It gives us an answer for C. It says there is no line or point of symmetry. So what word do we write here? If it doesn't have line symmetry or point symmetry, what should we write? Neither, yeah. Has neither line nor point symmetry. You can't fold it onto itself. You also can't flip it over and have it be the exact same function. All right, next one. It tells us we have point symmetry, okay? What is the point of symmetry? What are the coordinates of the point of symmetry? At what point could we flip this 180 degrees and have it be exactly the same on both sides? I guess another question is, where's the middle of the graph? Where's the middle of the function? Middle of the function. What is that? 0, -2. Yeah, that's exactly where it is. So the point 0, -2 right here, basically it's where the graph goes from coming up this way and going, what would be the way to say that? Because it's always increasing. I'll try to think of a better way to say that. What's that? I guess, yeah. No, I mean, that doesn't, I mean, in this case, yes, but in other cases, it won't necessarily be that way. I don't know. I guess the middle, I'm going to put that in air quotes because that's not technical, but like the middle of the graph is where the point of symmetry is, which is at 0, -2. I'm sure there's a much better mathematical way of saying that. All right. Any questions so far about A, B, C, or D here? I think the next page is the last page. Yeah, we're getting close. We're almost done. So this is a much quicker lesson than the first one. Hopefully it's a little bit easier to understand as well. That would be nice. Okay. Identifying even and odd functions. Okay, so determine whether each function is even, odd, or neither. Confirm algebraically. If the function is even or odd, describe the symmetry. First of all, if it's even, it's going to have line symmetry. If it's odd, it's going to have point symmetry. Like we were told that on the last page. So that's hopefully be an easy answer at the end if we determine one or the other. So this one, looking at it, it appears that there is symmetry around the origin. Rotational or line? Would it rotate to look the same, or would it reflect to look the same? Rotate. So chances are we're going to say this is weird. So I guess we can assume right now that this is an odd function because it looks like it has point symmetry in the middle of the graph. To prove that, we are going to use the function f of x is equal to x cubed minus 4x because that's what the graph is. So it says it appears that f of x is symmetric about the origin. Substitute opposite x for x to test this algebraically. What this means is, instead of writing f of x equals x cubed minus 4x, we're going to write f of opposite x is equal to opposite x cubed minus 4 times opposite x. That's what we're going. So, and I'll do a number example as well, just to show you with numbers, but we're going to use like just pure algebra for the moment. And so everywhere you see x, you're going to substitute in opposite x or negative x. All right. Now, if you cube a negative value, negative x times negative x, negative times a negative is a positive, so that would be positive x squared, but then you multiply it by another negative x, positive times a negative is a negative, so that would be negative x cubed. That's that value right there, or opposite x cubed. And then over here, opposite 4 times opposite x, negative times negative is a positive, so that would be positive 4x, so plus 4x. And then what it's doing, it says distribute, but technically I guess we're factoring. We're factoring out a negative 1. And if we factor out a negative 1, basically divide each of these by negative 1. I'm just going to do that little division here, I'll show you what's happening. So if we divide this by negative 1, we divide that by negative 1. We end up with a negative 1 here, or just a negative. And a negative divided by a negative is a positive, so that's positive x cubed. And a positive divided by a negative is a negative, so that's negative 4x. Now, x cubed minus 4x is the original function. That is this. But now we have a negative on the outside, which means that we have a negative function of the original value of x. I'm going to go back and show you on the last page what we're talking about as well. But if you place an opposite value of x to the original value of x, you should get an opposite value of y for the original value of y. That's what we're saying here. So if we go back, if you place an opposite value of x into the original function, you get an opposite value of y for the original value of x. Using numbers. Let's do this with numbers, so maybe it'll be a little bit clearer if you're having a little bit of trouble. So let's pick a point on this graph that is not in the middle of the graph. So a nice point looks like, I'm going to pick one, and it appears to be one that isn't. Let's go with, the only one that I can see that isn't in the middle of the graph is negative 2, 0. All right, so negative 2, 0. So if we use a value of negative 2 for x, let's just plug it in here. So I'm going to draw an arrow over this way, and I'm going to say f of negative 2 equals, we're going to plug negative 2 in for the function over here. Negative 2 cubed minus 4, my red pen's not working very well, times negative 2. So we're substituting in, come on, pen. All right. And so we're just going to evaluate the right side here. So when x is negative 2, what's the y value on the graph here? 0. So what number should we get when we evaluate the right side of this function? What is negative 2 times negative 2 times negative 2? Negative 2 times negative 2 is positive 4. 4 times negative 2 is negative 8. We're actually doing math today. All right. Like real calculations. Okay, so f of negative 2 is equal to negative 8. And then what's negative 4 times negative 2? 8, positive 8. What's negative 8 plus 8? 0. So f of negative 2 equals 0. Now, this isn't the best example because our value for y is 0. What's the opposite of 0? 0. It's itself. So if we were to use the opposite value of x that we just used, which would be positive 2, we should get the opposite value of y, which would still be 0. But let's see what happens. So f of 2 is equal to 2 cubed minus 4 times 2. So if we plug in the opposite value of x, we should end up with the opposite value of y, which in this case would be the same value of y because 0 is its own opposite. 2 cubed is 8. Negative 4 times 2 is negative 8. So 8 minus 8 equals 0. So opposite values of x produce opposite values for y. That's what we got going on. That's exactly what we're showing here. If everything here is x, everything here opposite x, an opposite value of y, I mean, if you think about f of x being equivalent to the letter y or the variable y, if you have a positive y here, positive f of x, you'd have a negative y here, negative f of x. So this is y, this is negative y, positive y, opposite y, whatever it is. So because f of opposite x is equal to the opposite of f of x, the function is odd and is symmetric about the middle of the graph, which is called the origin. Any questions about that? We'll process before we continue. The algebra here is probably going to be the hardest part of it, I would say, because you will have problems where you're going to need to do some algebra with that without actually plugging in for values. So be prepared for that. Let's try the next one. Graph of b is g of x is equal to 2x to the fourth power minus 6x squared. It appears that the graph of g of x is symmetric about the y-axis. Like if you fold it this way across the y-axis, it'll end up mapping onto itself, which implies that it's going to be an even function. And so if we're going to check for an even function, we're still going to replace x with the opposite of x. Every time we check, you replace x with the opposite of x. However, if it's odd and you have a y value, you're going to end up with the opposite of that y value. If it's even, if you start with a y value, you're going to end up with the y value again, the same exact value. So if we plug in an opposite x all 3 times here, opposite x, the value of y here when x is positive should be equal to the value of y here when x is negative. The values of y should be the same. They should not be opposite this time. So negative x to the fourth power being negative x times negative x times negative x times negative x, which would be positive x to the fourth, so 2x to the fourth. If you multiply 4 negatives together, you get a positive. Over here, if you multiply 2 negatives together, that would just be x squared. But because this was a negative 6, and x squared times negative 6 is still a minus 6x. So whether you use x or the opposite of x, you still end up with 2x to the fourth minus 6x, which is the same thing as the original g of x. Positive x or negative x produces the same y value, which means that the function is even. And is symmetric in, we're going to say the y-axis, because it's symmetrical around that vertical y-axis. All right. Any questions there? Let's try another one. So it appears that this graph might be symmetric about the origin. It looks like if you flip it upside down, could be exactly the same. But we need to check just to make sure. So anytime you're checking to see if something is even or odd, take the original value of x, replace it with the opposite of that. So opposite x cubed plus 0.25 times opposite x squared minus 3 times the opposite of x. The opposite of x cubed is negative x cubed. We saw that with example A up top on this page. So negative x cubed. The negative x squared would be, or negative x squared would be x squared, because negative times negative is positive, times 0.25 would be 0.25x squared. Negative times a negative is a positive. 3 times x would be 3x, so that's plus 3x. All right. If we were to factor out a negative here, They didn't do that this time. I want to do that just to get that little detail in there. So let's factor out a -1. So everything here will divide by -1, divide by -1 all the way across. So if we factor out a -1, that's the same thing as factoring out a negative, which is just going to turn everything in here to its opposite value. And so this is going to equal the opposite of x cubed minus 0.25x squared, and then minus 3x. Does the stuff inside the parentheses here match the original function? Not quite. The first one is x cubed. The last one is minus 3x. The middle one, though, is negative 0.25x instead of plus 0.25x. So this opposite is not equal to the opposite of the original function. It's equal to the opposite of some other function that's really close to being the original, but not exactly the same. So because the opposite of h of x, which is this, that's what we just figured out, is equal to the one that we just had up here, or equal to this here. I like this better with the parentheses. The function is neither. It's not even, it's not odd, because, I mean, we can actually test to see if it's even or odd by doing that one thing. It's definitely not the same as the original. It's also not equal to the opposite of the original. Therefore, it's neither odd nor even. So none of those things are true. And so if something appears, and it actually says this on the left, watch out, even in odd functions, always confirm symmetry algebraically. You can always do it without plugging in numbers. You can always do it by plugging in the opposite value of x. Graphs that appear to be symmetric might not actually be. This one's really close to being symmetric, but it isn't symmetric. All right, last one here. Assume that f is a function that contains the point 2, -5. Which of the given points must be included in the function if f is even and if f is odd? So even functions mean that if we take the opposite value of x, we get which value of y? Same or opposite, if it's even? Same. If we take the opposite value of x, we get the same value for y. So if this is x, what's the opposite of that? -2. Same value of y would be -5. So we need -2, -5. That would be this one. So if it's even, we'd have the opposite value of x with the same value for y. If it's odd, what are we looking for? We're looking for both values that are opposite. So which one would that be? Yeah, -2, +5. That's this one right here. Do any of the other ones work? They don't. All right. That's all I got for you. Hey, look at that. We got some time. So pause this up. I'll let you know what your assignment is.